All right, welcome everyone to Chapter 7. This is further applications of the integral. Here we are in section number 2, and we're going to be discussing the area between two curves and then give you an idea of applications that this can be used for. So, up until this point, right, we've only been doing area between a function and the x-axis. And, as I promised at the beginning of Chapter 6, the second big topic was actually area between curves, right? And so it doesn't have to be just a curve in the x-axis, it can be any two curves. And so that being said, right, it's time to do an upgrade, right? I want to be able to figure out what is the area between any two curves, and so it's definitely, if you look at this last picture right here, this is what I'm hoping to achieve, right? Finding the area of this blue region right here, the area between F and G. And the idea is actually pretty straightforward. So let me go ahead and sketch in some areas that we would know how to find. So we already know how to find the area between a function like f here and the x-axis. So it would look something like this green shaded area. And we know how to figure out the area between another function, let's say my g function here, and the x-axis. So it's going to look something like this. And so the idea is that these three pictures are related, right? You can see that F actually has too much area. G has not enough area, right, in order to get this bit right here. And so if I was to calculate the area under F, in order to do that, you would do a definite integral from a to b of f of x dx. And then if I was to calculate this area of the purple region here, and this is going to be from a to b of g of x dx, right? In order to achieve this final picture over here, what I'm going to want to do is take the area that f has and then subtract away the area that g has, right? So if I was to try to sketch maybe this g function right here, so let's say this is my g function, and if I just very quickly sketch in this purple stuff, right, if I was to subtract away this area right here, what would be left is just the region that I want, the area between f and g. So that being said, I'm going to take the area that f has, I'm going to subtract away the area that g has, and in fact we know, because of rules of definite integrals here, that if you're subtracting two definite integrals like this, that you can choose to write it, right? Instead of having to calculate out two things, we could just calculate out one definite integral of f of x minus g of x. And this was the difference rule for definite integrals. So, that being said, here's the nice theorem. Here's when things apply, right? So if f of x is greater than g of x on some interval, ab, like we have up above, then the area between f of x and g of x on this interval is given by, well, exactly the formula that we arrived at up above. So f of x minus g of x, and it's always the big function, f, the taller function, right? What does it mean that f is greater than or equal to g of x? It means that the y values are bigger, right? So f of x's y values are bigger than g of x's y values on this interval. So when you subtract them away, you're still going to end up with a positive number. And then let me also emphasize something else for you here, that this is the area. And so we've dealt with a couple different area definitions, right? We've brought up net area, right? And that's a case, right? Sometimes area is counted negatively. Here we're just talking about area. And therefore, if I got a negative answer, I would be very worried, right? Because area in and of itself should be, a non-negative number. Area is something like, 5 square centimeters, right? It should be positive, or at very worst case, 0. So again, we're talking about area, so all of our answers should be positive. If you get a negative answer, this is a warning symbol, right? That we're doing something wrong, that we need to rethink the problem. Okay, so let's move on to actually try to calculate one of these things out. Find the area between p of x equals x squared minus 4 and q of x equals 2 plus x on the interval from 0 to 3. And so notice, it's given us the interval, that's nice, we have this a to b region, but I don't know which one's bigger than the other, right? Because the order definitely is going to matter here. So I need to figure out which one's bigger than the other, and there's a couple ways that you can go about doing this, but what I'm going to do is just graph it in my calculator, right? So I'm going to pull out my calculator, and I'm going to graph these two functions. So the first one I'm going to graph is the x squared minus 4, and hit graph and just stare at this one really quick. Remember, I'm only really caring about the interval from 0 to 3. Okay, so that's what that one is, and then I'm going to go ahead and graph my second one, so that's going to be 2 plus x, graph. And there you go, and you can see that they cross a couple times, but again, all I really care about is the interval from 0 to 3. And on the interval from 0 to 3, in fact, let me go ahead and maybe zoom in a little bit. I'm going to zoom in here around 1 or so. Oh, but now I can't see it up. All right, fine. I'm going to mess with the window then, right? So I'm going to actually just go from 0 to 3. Let's see, my y minimum, I will go from 0 to 5 or so, just in case. Actually, let me do 5.5. Okay, now let me go ahead and graph. Here we go. So you can see on this interval, the straight line is always bigger than the curvy one, right? In fact, we kind of lose the curvy one, the parabola-looking shape there around 2. It kind of goes below this x-axis. But you can see they actually meet up at 3. So this is a case where they're actually equal to one another. But on that entire time, q of x, the line, is bigger than p of x. So when I set up my area formula, this is going to be the integral from 0 to 3, right, because my interval, 0 to 3, of the big function, 2 plus x, right, this one's bigger, it has bigger y values, minus the small function. And notice what I'm doing with the parentheses here, right? A common mistake is that people forget to subtract away the entire function. And sometimes I see that this subtraction sign is only applied to the x squared and you forget to apply it to the negative 4. So it's very important that you do both. Okay, let's go ahead and do one line of simplification before we evaluate out this definite integral. So let's see, I have 2 minus negative 4. So that's going to be 2 plus 4, that's going to be 6. There's just one regular old x, and then there's negative x squared dx. Okay, so I've simplified this down, combined all my like terms. Now I'm ready to evaluate this out. I'm going to use the fundamental theorem of calculus here. So fundamental theorem of calculus, I need to figure out an antiderivative of this thing. So capital F, let's see, will be equal to the antiderivative. Let's see, in order to take the derivative and get 6, I would need something like 6x. In order, when I take the derivative to get x, I'm going to need something like x squared. But this is going to be wrong, right? This would be 2x. So I'm going to put a 1/2 here to cancel that out. And then minus, of course, this is going to be 1/3 x cubed. So this is just reminding us of our antiderivative rules, right? This is really the power rule that we came up with there in chapter 6. Okay, so I'm going to evaluate this. This is going to be f of 3 minus f of 0, again, according to this fundamental theorem of calculus. So let's see, if I plug in 3, everywhere I see an x up here, I'm going to have, let's see, 18 plus 1/2 and 3 squared will be 9. And then minus 1/3 and 3 cubed. Okay, 3 times 3 times 3, that's going to be 27. Okay, and now if I was to plug in a 0 everywhere I see an x, well, I'd have 0 plus 0 minus 0. Okay, so that one's pretty boring, right? So let's go ahead and evaluate this out. 18 plus, I can combine these, right? This is going to be 9/2, and then minus, let's see, 27 divided by 3, that's going to be 9. And okay, let me just use my calculator to kind of finish this up, right? So I'm going to go ahead back to the regular screen, and we have 9 plus 9, oops, darn it, 9, wow, I'm really messing up 9. There we go, 9/2 minus 9. Enter. All right, so positive 4.5. So again, a positive number that makes me think, okay, I'm probably along the right tracks. Okay, so 4.5, that is my final answer. Okay, and again, if I got a negative number, I would be worried. I'd probably redo this problem. Again, I'd probably have to switch these two functions right here if I got a negative number. Okay, so let's move on and see that these can actually get decently complicated, right? So I have a more difficult problem here. Find the shaded area. right? And so it specifies over on the right-hand side here my functions, y equals x plus 1 and y equals 5 minus x. But when you go to set up our area equation, right, you can see that sometimes this 5 minus x is on top, right? So this interval right over here, 5 minus x is on top, and then the x plus 1 is on bottom. So during this period, I would want to do 5 minus x, subtract away x plus 1. However, in the next region, right, it switches, right? And actually x plus 1 is on top, and I'm running out of colors, I guess blue, right? 5 minus x is on bottom. So we actually need to break up this definite integral into two pieces. And I'm going to calculate out the area of these, well, they're triangles, right? I'm going to calculate out the area of each triangle kind of individually. And so in order to do that, I need to know where do these things cross. What point is that right there? And of course, if you want to determine where points cross, right, this is not a very detailed graph right here. So I'm going to do it with the equations. I'm going to use the equations and just set them equal to each other, right? That's how you figure out when two graphs cross. And so let me add x to both sides, and I'll subtract 1 from both sides. And so I get x equals 2. So these things actually cross at x equals 2, and that kind of makes sense based on the scale of my graph here. So I'm going to first figure out the area of the blue triangle, right? So in order to do that, I'm going to do the integral from 1 to 2, right? And just figure out the area between the curves on this region. So again, during this region, we know that 5 minus x is on top of, right? It's bigger than x plus 1. So I'm going to set up this integral. And then, in order to finish this out, I'm going to figure out the area of the second triangle. So that's going to be between 2 and 4. And on this interval, right, again, the x plus 1 is on top. So x plus 1 is on top. And I'm going to subtract away 5 minus x. All right. So now let's go ahead and calculate these things out. First, I'm going to go ahead and simplify. Maybe I'll really emphasize over here, right? I'm calculating out the area of the shaded region. So let me first go ahead and simplify. So let's see. I'm going to have 5 minus 1, right? It's important that this minus goes to both. So 5 minus 1 will be 4. Negative x minus another x. So that's going to be negative 2x. Oops, I'm getting ahead of myself. Negative 2x dx, there we go, plus the area of the region between 2 and 4, between the curves x plus 1 and 5 minus x. So we have x minus negative x, so that's going to be x plus x, so that's going to be 2x. And then we have 1 minus 5, so that's going to be negative 4 dx. Okay, now I'm going to go ahead and calculate out some antiderivatives here. Some antiderivatives. So this one maybe right here, if I consider this to be little f, then capital F, my hand keeps on touching the side of the screen here. Capital F is going to be equal to 4x minus x squared. And then this one over here, this is going to be maybe g. So capital G, the antiderivative, or an antiderivative, will be x squared minus 4x. So according to the fundamental theorem of calculus, this is going to be f of 2 minus f of 1. And then over here, this is going to be g of 4 minus g of 2. Okay, so now all I have to do is plug these things into my function. So 2, when I plug in 2, I get 8. Let's see, and I'm still plugging in 2, so 8 minus 4. Subtract away, and when I plug in 1, I'm going to get 4 minus 1, right, because there's two terms. And then over here, if I plug in 4 into my function, right, I'm going to get 16 minus 16. That's pretty boring. Okay, and when I plug in 2, I don't know, I'm a little bit paranoid here. 16 minus 16. Okay, yeah, that's fine. And then when I plug in 2, I'm going to get 4 minus negative 8. So 4 minus 8. Sorry, getting ahead of myself here. Okay, so again, plugging in 2 into my g function, right? So 2 squared, 4, and when I plug in 2 here, this becomes negative 8. Okay, let's go ahead and simplify down. We have 4 minus 3 plus 0, and then this is going to be negative 4, so plus 4. So altogether we have 1 plus 4, so that's 5. So actually this right here is going to be the area of my first triangle, over here. Kind of barely see my highlighting. And then 4 is going to be the area of my second triangle, which makes sense. It's considerably bigger, right? And so altogether we have an area of 5. So that's my final answer, 5. Okay, so as you can see, right, it's kind of hard if the functions crisscross, right, if they go on top of each other and stuff like this and kind of switch. So therefore, I'm going to give you an upgraded theorem here. So this no longer specifies which one's on top, right? F can be on top, G can be on top, whatever, right? And then we're going to go ahead and still specify the interval from A to B, and we can calculate out the area in this case by doing the integral from A to B of the absolute value of f of x minus g of x. So this says no matter which one's on top, right? Let's say, you know, g of x is accidentally on top or something like this, then you would get a negative number, right? But then this absolute value is going to make it positive. So that's really nice. This works out. And so let's then use this to double check our work here in 2.3. So I'm going to pull out my calculator again. And so I'm going to use math. And then remember, number 9 is my fn int. So I'm going to try to figure out the area of something. And so the thing that I'm actually integrating is going to be this thing, right, with the absolute value and all. So I'm going to do math and go over to num to get abs. So absolute value. And f of x, remember now it doesn't specify which one's on top. So I can use either or. So the first one I'm going to do x plus 1. X plus 1. And then I'm going to subtract away g of x, right? And so let me use my parentheses here just to double check, right? So this is going to be 5 minus x. It's important that you do subtract away all of it. So close those parentheses, close the absolute value parentheses, and we're going to be integrating with respect to x, and we're doing this on the interval from 1 to 4. 1 to 4. Okay, close that up. Hit enter, and if things work out correctly, we'll see the number 5. Okay, so it's a little bit off. Again, the calculator is approximating these things, but very, very close to 5, right? So our actual answer is 5. Our way is a little bit better, actually, than what the calculator is doing here. Okay, so this is, again, a nice way that we can use our calculator to check our work. As promised, this actually has some applications, right? So my final example that I would like to go over with you guys, 2.5, consider the marginal cost and marginal revenue functions for the business shown on the graph below. How much more profit will they receive if they increase production from 100 to 200 units? So our rate of change, the thing that we want to measure, right, is how much more profit, right? So we want to add up maybe marginal profit. So, and I'm going from 100 to 200, right? So this is specifying my interval from 100 to 200. And I'm going to be adding up marginal profit for producing X goods, right? And of course, we know that marginal profit is the same thing as marginal revenue, so R prime of X, subtract away marginal cost, C prime of X, right? So those are the derivatives. And so this right here is actually the exact setup for area between R prime of X and C prime of X, right? So in fact, what we're actually figuring out is the area between these two curves, revenue and cost, on the interval from 100 to 200, right? So this is some real world, sentences and statements that say, really, we want to figure out area between curves. Okay, so now we can go ahead and set this up. So 100 to 200, I know my marginal revenue function, so I can go ahead and plug that in. That's going to be 6 plus 0.02x, so that's marginal revenue. Subtract away marginal cost, that's up here, so 0.001, x minus 150 squared plus 3. Close parentheses dx. And okay, so in this case, let me actually use my calculator to evaluate this out. You can notice that we're safe, right? The r prime of x is on top, right? The revenue is the bigger function than the marginal cost on this entire interval. So you don't have to worry about absolute values or anything like this. So that being said, let's go in and I'm going to do math. Number 9, fn int. And so I'm going to be integrating the function 6 plus 0.02x minus, and now let me do parentheses here just in case. And so this is going to be 0.001 times parentheses x minus 150, close those parentheses and square it, plus 3. And now I'm going to close my parentheses from the subtraction. I need to specify which variable we're integrating with respect to, so comma x, comma, and the range is going to be from 1 to 200, right? So 100, comma, 200. And then close the final parentheses, hit enter, and there we go. So we have 516 plus 6667, and so let's see, I'm going to go ahead and write down 516.67. And remember, we want to think about units, right? So this is our units right here. I mean, these are number of goods and stuff. And here we have dollars per unit, right? Produced and sold and stuff like this. So this right here, the units are going to be just dollars, right? Because you can kind of think about multiplying the X units, which are just units, with the Y units, which are dollars per units, right? So these unit things cancel out, and all you have left over are dollars. So $516.67. So again, the question was, how much more profit will they receive if they increase production from 1 to 200 units? They will profit $516.67 more if they increase that production. All right, so now you can see that, again, area between curves can really be used for something. So this is where we're going to end. We'll go over some more examples in class. I'll see you then.